This is video 43 in the lecture on the design of reinforced concrete beams. This lecture deals with design of prestressed concrete in SLS, and we will look at the load balancing method. Consider an infinite decimal small piece of tendon over an angle of d alpha with a radius of the tendon profile of r, which is constant. The tension in the tendon is P, and the force P is in equilibrium with the upwards pressure against the concrete in Q kilonewton per meter. The angle is d alpha over 2 and d alpha over 2. Now we will make a vertical translation equilibrium, action against reaction. The action is P times the sinus of d alpha over 2, which is upwards force, plus on the other side also P sinus d alpha over 2, and this must be in equilibrium with the reaction against the concrete, which is Q times R d alpha, the length of the tendon. For small angles, d alpha over 2 is small, then the sinus of d alpha over 2 equals d alpha over 2, and then the equation leads to that the uniform distributed load equals the tension in the tendon P divided by the radius R. So Q is P divided by R. It means that the prestressed forces applied to the concrete can be simulated by an external uniform distributed load equal to the prestressing force divided by the radius of the tendon profile. We will give an example of an isostatic beam with a parabolic tendon profile, and where the tendon profile or the eccentricity of the tendon profile is 0 at the support and is F at midspan. The equation of the parabol is then equal to what is written here. When the eccentricity for x 0, if you make x 0, then EP of 0 is then 0. The eccentricity at the end of the beam when x is equal to L is then also 0. That's the thing that we wanted to have. And the eccentricity at midspan at L over 2, if we calculate that with this formula, we have F, and this is what we wanted. So this is the equation of the profile of the tendon between 0 and L, for x between 0 and L. The radius of this profile, this radius, this circle radius, is then equals L squared over H 8F. This was the equation of the profile. The bending moment induced by the pre-stressing force P is then equals to P times the eccentricity. If we take the first derivative, the m over dx, then we have this expression, but this means this is equal to the shear force. If we have the second derivative, then we know we have the uniform distributed load. So this minus 8F over L squared times P equals the distributed load minus Q. So this means that this system can lead to an equivalent force system where the pre-stressing force is replaced by a uniform distributed load with the value of P over R and two forces at the end at the supports. The vertical equilibrium should be 0. So if we look now at the shear force at the first support, So that's dp over dx with x equals 0, means that the shear force at the beginning, at the first support, is 4pf over L, and the reaction caused by the uniform distributed load Q is QL over 2, of minus QL over 2, and the Q and the Q is then P over R, sorry, is PL over 2R, and then we can replace the P by this expression, and we have minus 4pf over L. So then we see that V equals minus R. So the shear force at this point created by the bending moment caused by the pre-stress force equals the reaction force of the reaction at the support created by the loads Q. A tendon profile is then built up by a series of segments with a constant radius R. So this is a tendon profile with a variable eccentricity. It has a segment with a constant radius R1, a constant radius R2, from there from P1 to PT2, from P2 to P4 it's a radius R3, and so on. And each segment with the constant radius can be replaced by an equivalent force, a uniform distributed load, and Q1 is then equal to P, the pre-stressing force, divided by R1. Of course, the arrows here must show upwards instead of downwards, and this should show downwards. So the load case pre-stress can be replaced by an equivalent system of equivalent distributed loads equal to P over Ri. Take an isostatic field with a single radius tendon profile. Single radius, it means one radius for the whole profile of the tendon. If we look for the equivalent loads, then we know that the uniform distributed load is Q is P over R from down to up, because the curvature is this way. We replace at the supports the pre-stressing force P, and the other force is LP over 2R. When we consider an isostatic field with a bilinear tendon profile, this is common used for Y profiles, prefabricated Y beams, Y-shaped cross-section beams. Then the first inclined portion is over distance A, the maximum eccentricity is E. If we look at this, then we can easily see that you can replace this by the forces EP over A at this point here, and the forces P and EP over A as it is shown here. So you will see that the total vertical equilibrium is 0. We can also have an tendon profile which is horizontal with a constant eccentricity E. Then in this case the equivalent system is a bending moment at the end, EP, and an EP there with the compressive force P. You can have an hypostatic field. It's clamped on both sides, and then when it's clamped, and this is a horizontal line, then you will see, because it's clamped here, the angle of rotation is 0. So you see that we have 1, 2, 3 radii in the tendon profile, and we can easily then draw up the equivalent force system. Q is then P over RA or P over RB, with the two forces P at the side. Because the inclination here is 0, you do not have another vertical force on the reaction. And this is the same, it's the end field. It's always the same system, but you must take care in the reaction. Okay, you can now design a pre-stressed beam with a load balancing method. See you next lecture.